Hi everyone. So let's wait for a few seconds and we can get started. Cool. I think in the last few weeks we were learning lots about convolutional neural network, especially related to images. And then we started learning natural language processing. And also we have learned something with tabular datasets. So far we have covered computer vision, natural language processing, and tabular datasets. But in today's session, we'll be focusing more on collaborative filtering, and we are in lesson 7 of. We'll be covering collaborative filtering models for recommender systems, and then after that, we'll be learning some few concepts related to collaborative filtering as well as some general concepts. So that's the structure of today's session. Cool. And before starting this session, let me talk about this one. So far what we are doing is covering the fast AI lessons. So there are 8 lessons. We are in lesson 7, still one more. And from October 11 onwards, there is a new course coming, which is a part 2 of fast AI. So this course is about from deep learning foundations to stable diffusion. So I already shared this link on our Slack channels. So if you are interested, you can enroll. And if you are an open source contributor, there are some scholarships for that. So all the details are here. You can check it out. Cool. Let's get started. So there are three notebooks to cover. So I'll be starting with collaborative filtering deep dive, this notebook. So I already shared this notebook on our Slack channels, so you can see it here. So this is the first notebook you can see something like this, and there is a button like copy and edit like this. So if you click copy and edit, it will open environment for you. Yeah, it's starting up. So here you can see it's a GPU and internet is on, so that so that you can run everything. Shift enter to run. So likewise, you can run everything on collaborative filtering notebook. So I'm going to start from here. So collaborative filtering models is mainly used in recommender systems where you can recommend anything like products, movies, books, and many more. You can recommend one is movie. So you have user ID and you have movie ID. And for this user, for this movie, the person used rating 3. So likewise, you can see for this user, for this movie, the person rated 3. So likewise, you can see all the data. So generally, we need three things. One is user and any item. In this case, it's movie and some rating. Sometimes, let's say you don't have rating, but you know the details about whether someone used that product or not, or they bought those product or not. In that case, you can use 1 and 0, and then we can train a model. So for our project, we'll be using movie lens dataset. So this movie lens dataset has 4 things: user, movie, rating, timestamp. So we are loading that. So so here we are trying to change the structure to see how it looks like. So if for this user 14, he has watched all these movies and this is their rating. And if we see user 212, that person watched most of the movies, but he didn't watch, he or she didn't watch this movie and this and this. So what we are trying to do is we are going to use this dataset to learn something from this dataset. So what I mean is for each user, we randomly allocate some numbers, and then for each movie, we randomly allocate some numbers. Then we multiply those numbers, which is a dot product, and then we calculate some loss. Then we can compare that loss with these given values, and then we can update those weights and biases that we randomly initialized for users and movies. So what I have thought is just a high level, but we will be diving into each concept as we go. Okay. So the project is about, we have user details and we have movie details, and we have some information like whether this person rated, what's their rating. So that's all. We know only 3 things. From these 3 things, we are going to develop a model that's going to predict the rating for all the movies. So before starting this, how we are going to tackle this is, maybe let me give you some example very similar to this one. So let's say we are going to recommend books. Oh, sorry. So let's say person 1. So this person 1, let's assume his ID is 4, and for this person, we are going to find some information about this person. Ideally, we are going to find 3 things. First thing is, let's assume whether this person likes PyTorch book, how much he likes PyTorch. This is 1. And second is, let's say this person likes PyTorch book very much. So we are going to assign a high number. And the second information we are going to find is whether this person likes practical books. Let's assume this person likes hands-on practical books. So let's assume a high number, 0. And the third thing we are going to find is whether this person likes old books or new books, latest books. Let's assume this person likes latest books. So we are going to assign some high number. Okay. So this is person 1. And let's use one more person. Person 2. Let's assume his ID is 8. And for this person, he does not like PyTorch book. So we are going to assign some low number, 0.2. And let's assume he likes practical books, 0.8. And let's assume he also likes recent books. And let's do one more user. His ID is 16. And let's say he doesn't like PyTorch, and he doesn't like practical books. He likes only theoretical books. And let's say he likes to read old books, like the books published 10 years ago, something, or 5 years ago, something like that, which is pretty old compared to deep learning. So let's assume some low number. So let's say we have these three information for these three users. And now let's assume I have 2 books. Or let's assume I have 3 books. Book 1, Deep Learning with PyTorch. And book 2, Deep Learning by Goodfellow, which is a theoretical book. And book 3, Deep Learning with Python. I think this book is about Keras. Okay. And let's create 3 numbers for these books. So the first question is whether this is a PyTorch book or not. So this is a PyTorch book. So we are creating a high number, 0.9. And second thing is whether this book is practical or not. This book is really hands-on. So we are going to assign some high number, 0.88. And third is whether this book is latest. This book is latest, like released 2 years ago. So let's assume 8. So we got 3 numbers. And for second book, this book is not PyTorch book. So I'm going to assign a low number. And this book is not practical book. So this is low number. And this book was released like 7 years ago. In that case, let's use. And this book is practical, it's recent. Again, high number. So we got 3 things about books and 3 things about users. So how we are going to recommend is we can multiply each things. For example, I'm going to multiply this with this number. I mean the entire thing with this one. So it should be 0.9 multiplied by 0.9, add 0.95 multiplied by 0.88, add 0.88 multiplied by 0.8. Let's say I'm getting like let's say I'm getting like 2.3, some random number. Okay, I'm not calculating it, just a number, 2.3. Okay, so this is for book 1. So we are calculating for book 1 2.3. Let's assume for book 2, since the numbers are very different, 0.9 multiplied by 0.3, 0.95 multiplied by 0.2, 0.88 multiplied by 0.3. Let's say we are getting for book 2 1.1. For person 1, for book 3, let's assume we are getting 1.8. In this case, the highest number is 2.3. So we recommend the first book to this person. So what we just did is we randomly create, in this case it's not a random, we try to calculate some features like whether the book is PyTorch book, whether the book is practical, or whether the book is released recently or not. So we come up with our own features. So we have come up with just 3 features, but generally we can also come up with many features, as many features we like number of pages in the books, and which year exactly was it published, and how many 5-star rating in Amazon. So we can come up with many features. Cool. So now there is two things clear. One is we need some features like this 0.9, 0.95, 0.88, and then we multiplied that with products, in this case books. Then we get some number. Based on the highest number, we assign we assume that this person likes this or not. Okay, this is the some high level overview of dot products and what's happening in collaborative filtering models. Now coming back to our problem, we have three things. User, let's say users are 1, 2, 3, 4, 5, and movies. Let's say movie IDs are 99, 97, 93, 94. Let's assume this person watched this movie and he has given rating 5, and he likes movie 97, 5. He likes movie 93, 4. He doesn't like movie 94, 1. So likewise we are filling some numbers. Okay, so we got all these numbers from the data. So now what we are going to do is we are going to randomly create some numbers for each user, some random numbers. Let's say 3 numbers. Again some random vectors. Even for movies, we create a random vector. Then what we do is we just multiply this with this. Let's assume for this multiplication you are getting 3. Let's compare only this one, and this one. You are getting 3. Okay, but the real truth is 5. So you calculate the loss. 5, if you are using mean square error, so it is 5 minus 3, the whole square. The loss will be mean square error is 4 for that sample. So likewise, you can calculate the entire loss. Then you can back propagate and you update all these randomly created numbers. So initially it's random, but after training, those numbers will be very meaningful latent factors. So the steps are like this. For each user and for each movie, assign random vectors of length. Maybe let's use length 5. So generally we can use 50, 20 like that, but for simplicity I'm keeping it 5. Then do dot product. So we have already seen what is dot product. So in dot product you multiply each values with the corresponding. So let's assume this is our y prediction. Then you calculate the loss. The loss is y prediction minus y the whole square. Let's assume this is mean square error. You take average. Okay. Then you back propagate and update weights and bias. So what do you update is you update weights and biases, which mean the one we created random, those random numbers. All these random numbers will be automatically tuned. So with this background information, let's go to the data and we can understand more. So before that, let me quickly check if there is any question. Cool. So here for movie review for Lost Skywalker, we are finding three information. It could be anything. In this case, one is science fiction, and second latent factor is very action, and the third latent factor is very not old. And this is user's taste. Let's say this person likes science fiction movies, and he also likes action movies, and that person also likes very not old movie. I mean, he doesn't like not old movies, so that's why it's a negative number. But in this case, if you multiply all these things, we can recommend we will be getting like high number like this, 2.4, because those two vectors are in almost in the same direction. So this is all about dot product. So when we multiply two vectors together and add up the results, this is known as the dot product. It is used a lot in machine learning and forms the basis of matrix multiplication. So this is another movie, Casablanca, and these are three vectors. And for the same user, we won't recommend this movie because if you multiply, that's against their taste. So we are getting some negative numbers. So which is like an opposite of their taste. So we don't recommend Casablanca for that user, but we can recommend Lost Skywalker, which is very similar to what we have done with book examples. So we are going to learn the latent factors. So initially, for each user, we randomly create numbers. So these are initialized randomly, then we optimize them with gradient descent, which is model training. We use backpropagation to update weights and biases. So whatever we have seen in the previous tabular dataset, that same concept applies here. So here what we are doing is we are trying to, if you see the original data set, I think this is the, let me see. Okay, so this is the original data set. It has user, movie, rating, and timestamp. We don't need timestamp, so we will be having three information: user, movie, rating. So if we know what the movie is about, maybe that's useful while interpreting the models. So what we are going to do is we are going to merge the movie name with this dataset. So that's what we are going to do. Okay, so we got for each movie we got the title. We are going to merge that with ratings. After merging, you can see user, movie, rating, timestamp, and title of the movie. Now we can train a model. So we need to train a model, we need data loaders. So for this is collaborative filtering, we are going to use collab data loaders, and we have data frame. That's why we are using from df. Then we are passing the ratings. It needs two things, user and what is our item. In this case, the user column is already there, but there is no column name as item, but our item is title, so we need to mention item name is title. Then we can use any batch size. In this case, Jeremy used 64. And this is a batch result. We have user, title, and rating. Now let's see how many users are there. So let me find, and how many movies. So there are 944 users, and 1665 movies, and we are going to randomly assign 5 number for each user and 5 random number for each movie. So that's why our factor is 5. So we are using torch.random number random, and here we are giving number of users and we need 5. So after running this, check the shape. Okay, so we have 944 user, and for each user we assign 5 random numbers. So what we are doing here is to do the matrix multiplication, which is a dot product. We are creating one hot for person 3. So let's say we want to multiply this with all the movies. We can set this as 1 and remaining as 0. Then we can do a matrix. So this is the lookup of user factors. We randomly created some number, right? To look up those numbers programmatically, like in deep learning we do lots of matrix multiplication, so that's why we are doing it here. But generally what we can do is we can try to see user factors, and we need third user 3, which is same as this one. So this is a lookup. We are doing a lookup of the array, and here we are doing the same thing with one hot encoding multiplication to get the same lookup. And by the way, these latent factors, we call this as embeddings. In this case, these numbers are embeddings of user 3. So embeddings is just a matrix lookup of any array. That's it. So jargon embeddings. So multiplying a one hot encoded matrix using the computational shortcut that it can be implemented by simple indexing directly. So what we have done here is simple indexing, but it can be also implemented using matrix multiplication like this one. So this is quite a fancy word for a very simple concept. The thing that you multiply the one hot encoded matrix by or using the computational shortcut index into it directly. It's called embedding matrix. So now we are going to do collaborative filtering from. So our collaborative filtering model, which is just a dot product. So we have user embeddings. So let's say number of users, number of movies, and number of factors is given, and we are creating an embed. It will create 5 random number for each user, and the same applies for movies. So it will generate a random list, random matrix of number of factors with for each users as well as each movie. Then what you do is you just do a dot product. So here we get all the user matrix, and then we get all the movie latent factors. Then we do a dot product. So that is our prediction. Okay, so this is our model. Model is just a dot product, and this model will give you some model. So which random numbers are weights and which are biases? What is hot encoded matrix? Okay, the first question is which random numbers are weights and which are biases. So let's go back to this one. Okay, so whatever you are seeing it here, it's all about weights. We haven't added biases yet. We will be adding biases at the end of the section. So to go back here, these random numbers or weights, we haven't added biases. So let's say if you want to add bias, we add how many users. Based on how many users, we add some biases. So we will add that at the end of the section. So that's first question. And the second is, what is hot encoded matrix? So hot encoded matrix is this one. So let's say we have one hot. Okay. So let's say we need one hot encoding means, let's say we have got many 300 users and we want to get the user information of user 3. In that case, only user 3 is 1, remaining is 0, so that you can do a dot product and then get the user information like what we have seen here. So this is some user factors. All the user factors are here, but we are trying to get user 3 information, which is same as accessing that based on the index. So both are same. Why we are doing in one-hearted fashion is, in deep learning we will be doing lots of matrix multiplications. In that case, it's easier to do in that way than doing a manual lookup like this. I think the model is trained. So initially the loss is high. After 5 epoch, the loss is 0.88. So if you see this, the first thing we can do to make this model a little bit better is to force those predictions to go between 0 and 5. For this, we just need to use sigmoid range. So sigmoid range is a function that takes two number and then it converts all the data to the range in between. So let me explain that. So let's say you have user and some number 0.3, 0.4, 0.9, and for movie you have got three numbers 0.9, 0.9, 0.9. Let's assume we are getting like 5.99. Okay, some random number and you are getting 5.9. But generally in our case the movie rating is like 1 to 5, right? So we can convert this 5.9 to 5 and then we can use, in that case we can reduce the loss. But the easiest way to do that is we can apply a sigmoid function. So sigmoid takes any number and it converts to 0 to 1 range. Let's say you want output 0 to 5 means you can do sigmoid of some number multiplied by 5. If you do that, your output will be 0 to 5 range. Cool. So in one, it's very difficult to get those numbers because our weights, the number should be really high to get 1. So that's why we are using like 5.5, the given range. In this case, 0 to 5.5. If you do that, in this case, it improved a little bit, but not too much. Weights and biases here. So far what we have seen is, we have seen only this, and also we have seen these. But now what we are doing is, we are adding bias details to the model. So how we do that is, we randomly create weights, and for movies also we are getting some bias. So the intuition is, let's say user 1, and let's say he has watched these 5 movies, movie 21, 27, 28, 29. Let's say another user 2, he has watched, let's assume he has also watched these 4 movies. Let's say the user 1 always gives lower rating, even though he likes the movie really well, but he this is the person always, he won't give like a 5 rating. He always gives like 4, 3.5, 4, 3.5. And there is another person, if he likes the movie, he always gives like 5, 5, 5, 5. So what we are doing here is we are going to add a bias term. Okay. Oh, sorry. We are going to add a bias term for each user. Let's say the user 1, he doesn't give high rating. His bias will be like a low number, like 0.3, something like that. Let's say for user 2, he always gives a high rating for most of the movies he has watched. For him, the bias term will be higher, like 1.5, something like that. So this is, maybe I can give you like a little bit more on this. Let's say you have got X and Y. Let's say we are doing Y equal to X. Okay, so you will get a straight line. And let's say we are going to add a bias term, y equal to, in this case, mx plus b c. In this case, let's assume m is 1. Let's assume the bias is 2. If you do that, we will be adding 2 to all the numbers. So our new number will be a little bit higher. It shift all the points. This shift is explained by bias, and this direction is explained by the weights. Let's say if someone always gives higher rating for all the movies, we can increase their bias. So we no need to do that. The model will automatically figure it out, and it increases the biases for that person. I hope this is clear. What is the embedding class? Let me go back to this one. Okay, so here what we are doing here is for each, okay, this can be implemented using embedding class. In embedding, you can use the same n users and n factors. Let me do that. And you have got embedding matrix with 944 and 5. The same data, 944 and 5. And we can do some lookup. Let me see. I think there's a function to get details. So you can see it here. This is a same shared by both the NN module and script module, and this is which is creating some random number. Sorry, random norm. This is random norm. We are getting the same here, truncated normal, which is a normal distribution of numbers. So I'll try to see how to get some values from here. So let's use the embedding object is not subscriptable. First area, I think there is a way to access. Not sure if my internet is super slow today. I hope the streaming is good. Usually it won't take this much time. Or let me see this one. I think there's a way to access embeddings. We are doing it here. We can access like this, top IDX. In this case, it's a tensor. Maybe let's use tensor to get something. Or let's figure it out at the end of those sections. Anyways, we'll be doing that. We'll see how to access embeddings from there. Okay, so here we have users, which is user embeddings, and we have movies embeddings, and we are doing a dot product. And then after that, we are adding user bias as well as movie bias. Then we are doing the sigmoid range to convert 0 to some number, in this case 0 to 0 to 5.5. So with this approach, the loss didn't improve too much. After adding bias, it didn't improve, but there are a few ways to make it work. One way is doing some regularizations. So weight decay or L2 regularization consists in adding to your loss function the sum of all the weights squared. So let's say we have got some weights. We are going to square those weights and add it with some lambda, which means we use a coefficient to scale it down. So that prevents overfitting, because if the weights are really huge, means if you square it, the number will be really high. And since we are adding that to the loss function, the loss function will try to reduce the loss, right? The only way it reduces the loss is to get those weights to really minimum numbers, those weights. So the weights will be distributed equally, and no weight will be like really huge. And you can see it here. So what we are doing is there is a weight decay parameter. We assume some number, we set some number like 0.01 to scale all the parameters and its sum. So in this case, the parameters, all the weights, then we square, then we sum it, then we multiply that with some weight decay. Since we are doing it in the loss, anyways, in gradient descent, we will take the derivative of the loss. So instead of doing it here, we can also do that in the gradient update. In gradient, we can add this as 2 multiplied by parameters, because x square, if you take derivative, it becomes 2x. So that's why it's 2x. And after doing this trick, the loss is improved so much, from 0.88 to 0.82. I think, yeah, let's talk about this one. I think we'll find it. So what we are doing here is we are creating a tensor module. Here we are setting torch.1 says 3, and here there is no parameters, because we haven't set this as a parameter, because this is just a normal normal tensor. So if you wrap this with nn.parameter, you will get the tensor, you can get the parameters. So the model uses these parameters to update its weights and biases. So you just need to wrap this with nn.parameter. But if you're using something like nn.linear, those parameters will be automatically given in these classes. So you no need to do that. You no need to use nn.parameter. But if you're using nn.linear, we can directly access the parameters like this. Okay, so here we are creating lots of parameters with size, the given size within the range 0 to 0.01, and we are using that as embedding. So without embeddings, we are going to use this tensor, I mean the parameter, directly. Okay, the mistake I made is embedding. I try to ask subscriptable, that one. Let me, yeah. So it's a function. So instead of doing this, what we can do is you can wrap like this. Then you will get it. Yeah, you are getting some values. So this is embeddings. So embeddings is same as creating something like this. So that's a common mistake I did. Okay, I hope this is clear, Tim. Cool. Yeah, we can access from embedding.wait too. And if you're doing embedding.wait, you can access by square brackets. You can index that. Let me do that. Yeah, which is same as this one. So you can use square indexing for wait, but if you're directly using the embeddings, you need to wrap it as a function. Cool. Since we have trained a model, and the model highest loss is 0.81, which is better than all our previous things. Now we are going to interpret those weights and biases and see if there is any good pattern to learn. So one thing is we can find there are some movies where people always gives low value. So let's try to find that. To do that, we can access the movie bias and see the lowest 5 numbers. Okay, in this case, these are the numbers. So, okay, here are the movies with the lowest values in the bias vector. So for these movies, people always gives low ratings. So you can read this, think about it, what this means. What it's saying is that for each of these movies, even when a user is very well matched to its latent factors, which is as we see in the moment. Okay, they still like it. We could have simply sorted the movies directly by their average rating, but looking at the learned bias tells us something much more interesting. It tells us not just whether a movie is of kind that people tend not to enjoy watching, but that people tend not to like watching it even if it is of a kind that they would otherwise enjoy. So which is a great insight, right? Even though things. So again, this makes sense. All great movies. Cool. So now what we are going to do is huge, like I think D. So since we cannot visualize 50 dimension, we are going to apply PCA to reduce it to low dimension. So we have taken the movie weights and applying PCA. So it becomes a lower dimension, 3 dimensions, factor 0, 1 and 2. Then we can visualize those factors. In this case, Jeremy visualized factor 1 and 2. So you can see it here. I think okay, in this case, he visualized factor 1 and third factor. I don't know why. We can change this to 1 and see what happens. By the way, Fastai also has a computational linear algebra for coders. It's a great course. Cool. So here you can see some groupings. So if the movies are very similar, means you can see they are grouped together. And you can play with it. Let's use first and third and see what happens. Okay, here you can see the relationship between each movies. You may find this interesting for other data sets too. So whatever we have done so far, we have created our own classes like this and we trained a model. You no need to do that. We can directly use Collab Learner for this purpose. So in Collab Learner, you can pass your data loaders and then you can say how many latent factors we need and what will be our Y range. Then you can train a model. You will be getting very similar results, 0.817. Even here you are getting like 0.817, which is same. And you can access all the weights and biases by using learn.model. And to access user weight, you can use dot user weight. And to access item bias, you can use dot item bias. Yeah, you can see it here. The same results. Then since we know the embeddings of each movie, we can find most similar to those movie, and also we can do the same thing for users. We can group similar users like that. For that we are using cosine similarity. Here we are trying to find which is the closest movie for this one, Silence of the Lambs. So according to the model, it says Before the Rain, this one. I think we are pretty much done. Here this is not covered in Jeremy's sections, but this is written in the book. So here we use a deep learning based model, because since if you see our model so far, we are just using user vector and then we are using movie vector and we are doing a dot product. So instead of doing that, we can also add a few layers so that it will learn some complex patterns in the data. So which is very similar to deep learning approach. So you can see it here. We have a user embeddings and you have item embeddings, movie, and then we are going to combine both, and then we are adding non-linear functions. Then we are adding again a linear function. Then finally we'll get some output. Then the same after training didn't improve too much. Cool. I think we have covered most things in collaborative filtering. Now let's quickly move to the other. Yep. Okay, cool. So I have also shared two notebooks, part 2 and 3, these things. we'll be quickly covering these two. Okay, so here what we are going to see is we are going to learn some concept like gradient accumulations. So we are going to learn these four concepts: gradient accumulations. I think we already covered weight decay, and we are going to learn cross entropy loss, and we are going to learn how to solve multi-target models. So which means by using same single input, we are going to find two outputs, and we are going to optimize the models. You have model, you pass the data and it makes some predictions. Then by using those predictions and the truth, you calculate the loss. So this model has gradient descent update, stochastic gradient descent. Then these model weights and biases will be changed to reduce the loss. So generally, let's say you have got 1,000 images. Let's say this is image classification. So you have got 1,000 images. So I'm using a batch size as 16. In that case, I use 16 data first, and then I calculate the loss. Then I update weights and biases. Then after updating the weights and biases, I set my gradient as 0. Okay, so that it won't accumulate. Because we have already updated the weights and biases, so we need to start the gradient as fresh. So in the second iteration, it takes the next 16 data, then it calculates the loss, then it calculates the gradient of weights and biases with respect to the loss, then it updates weights and bias. Then you do gradient 0 to avoid accumulations. Okay, this is the general step. Now let's say you want to train a model with batch size. Let's say you have got very minimal GPU, and still let's say you want to use batch size 16. Okay, but now let's assume your computer won't fit batch size as 16, because so what you do is you use 8 images, and also let's say you want to do the same thing whatever you have done for 16. So what you do is you use 8 image and calculate the gradient. Then you won't update the gradient, you just use the next 8 image and pass the model and calculate the gradient. Let's say this is gradient 1. Then second iteration, this is 8 data, and there is another 8 data. You have gradient 2. Then you add both, sum. Then this is your overall gradient. To calculate the average, you divide it by overall sample. In this case, 8. We already do that. Since we are doing it 2 times, we divide it by 2. So after updating, then you can set 0. You can understand more. So this is the general step. You calculate the gradient. After calculating the gradient here, you update the gradient here. Then after updating, you set the gradient to 0. So the next time you will find the proper gradients for the new data. To avoid gradient accumulation, we are doing it. Okay, but now let's see what happens if you are doing accumulation. Here's the same thing, but with gradient accumulation added. Assuming a target effective batch size is 64. We are setting count as 0. Then let's assume in this case the batch size is 32, something like that. Then we calculate the gradient. Once you do the same gradient again and again, the gradient accumulates. But now once it crosses the count as 64, count is greater than accumulation target. So do weight update. So we will be doing weight update. After updating the weight, we set the gradient to 0. So this is to avoid the memory issue you can do the gradient accumulation to do that. And if you follow this, and for that we are getting, I think I need to run this to get the number, but I hope you understand the high level concept. You can run this and see how it goes. So that's gradient accumulation. Now let's talk about the second concept. Okay, the second concept is test time augmentation. So TTA means test time augmentations. So generally in machine learning or in deep learning, let's say you're doing some computer vision, you try to augment your input image so that for each training time, the image will be like tilted or added some brightness, and you will see a new image every time, like slightly modified image, so that it generalizes well, and you'll get some better results. So that's a general concept. But what's happening in test time augmentation is, instead of, let's say you have got some input image, let me quickly write this. Okay, so let's say you have got a some picture. Okay, so we are making some predictions. Let's assume this is cat, and you are getting some probability of cat is 0.88. So this is what you usually do is inference time. Okay, but what happens with test time augmentation is, you will, let's say you will create 4 test data set of the same image. In each time you augment your original image. Maybe in this case the cat is moved to the right side, and in the second one you add more brightness, and likewise you augment each image. Then you will calculate the probability. In this case, let's say the first image is like 0.9 cat, 0.92 cat, 0.72 cat, 0.85 cat. Then you sum everything. Then you and average. Let's say you are getting like 0.88. Then you say this is 80%, 88% chance this is a cat. So while doing this, your model will be generalized better, because you are not using a single image to make some predictions. You are doing some augmentations and creating many images, and you are making some predictions. So that is test time augmentations. Okay, I think the final concept is cross entropy loss. Let me write that. Okay, cross entropy loss. Okay, so here let's say you have an image and you are trying to predict whether this image is cat, dog. Input data, then you pass the input data to many layers, and finally you will get a 3 number. Let's say the first number is 2.3, 1.1 minus 2.8. Okay, you got 3 numbers, and let's assume this is cat, this is dog, and this is elephant. And for simplicity, let's assume this is cat picture. Okay, so you'll be doing lots of multiplications. After doing lots of multiplication for this number, so what you do is you take exponential of each number. Maybe let me write the formula first. E power x divided by sum of e power x for all the data points. Let's say there are 3 data points. For 3 data, you'll be taking exponential and divided by sum of all the exponential. Okay, so in first case, what you do is e power 2.3 and e power 1.1 and e power minus 2.8, and you divided by the sum of e power 2.3 plus e power 1.1 plus e power minus 2.8. Then you repeat the same, the bottom will be similar. And here also the same. Okay. While doing this, your final output should be a number between 0 to 1. Oh, sorry. 0 to 1. Let's say for here you are getting 0.7, and here let's say you are getting 0.2, and here it should be 0.1. And if you sum everything, it should be 1. So we are converting your logits to a probability, and we call this as softmax. Then to calculate the loss, let's say this is a cat image, we take the cat probability, in this case 0.7, and you take a log of 0.7, you will get some number, and you multiply that number with minus, because log of, let's say you are getting 0.2, this is your loss. Okay, so this is the loss of single data point. Likewise, you repeat the same step many times for all the data, then you take an average. So that could be your cross entropy loss. I think with this intuition, we can stop here. Maybe in the next session, we'll be learning more about binary cross entropy loss and all these loss functions one more time, more clearly. Thanks everyone. See you all next time.